So last lecture we were talking about spatially extended dynamical systems, and mostly it was introducing some terminology and trying to get you to think about what are essentially infinite dimensional systems and how they form patterns. Now, it was easy to see that they were forming some kinds of patterns because we were looking at them in one-dimensional space and time. What I wanted to do and I was, in a fairly intuitive way, arguing that some of the ideas and concepts from dynamical systems were relevant. Thinking about fixed points, could there be attractors, a notion of stable invariant sets, and so on. So I just made that a little bit plausible, and we were looking at these very, very simple, like the simplest spatially extended systems, the cellular automata, right? One-dimensional lattice, the state at every site is on or off, black or white. And most of the ones we looked at were radius 1, namely that every site looks to its neighbors, and then there's some uniform logic function gets applied over the whole lattice simultaneously to update every site's value. And even then, there's interesting sort of open questions in studying cellular automata, but they've been studied quite extensively. They were introduced in the, I guess the 1950s by Stan Ulam and John von Neumann, mathematicians at Los Alamos, in a very kind of exploratory mode. So what I want to do today is finish up with some demonstrations of cellular automata, and then we're going to talk about changing the local dynamical system to be continuous state, namely one-dimensional maps, but still on a discrete time, discrete space lattice. So what I didn't... last lecture, I gave you some sense of the range of pattern phenomena, and I very quickly talked about, I didn't formally introduce the notion of invariant sets, but sort of argued that there were certain regions of space-time, patches, if you will, of textures that came back to themselves. And that was mostly in the simulations just apparent visually. We weren't doing any sort of mathematics or trying to solve for fixed points or anything like that analytically. We don't quite have the tools for doing that, so I hope to come back in the early spring to this question of how can we represent invariant sets in cellular automata. We'll have more refined tools and have introduced some ideas from the theory of computation, in particular finite state machines. That'll make that more easier to represent. So last lecture was about phenomenology of CAs. Didn't change too much. Maybe it was a little richer if we went to next to nearest neighbors, so two neighbors on either side. But we still had this decomposition into statistically uniform textures and then breaks between them. We call them domains and domain walls. So I want to make a final comment on cellular automata, and then we'll start working with map lattices. I'm going to do this through simulation. So there are two different views here. One is, I should say there are three views. The view I've been using is the space-time diagram, right? So I just start at time 0 with an arbitrary bit configuration for the local states at each site, and then I just show you what happens when we apply the global update. That's big phi over time. Oops. And we can, let's see here. There we go. And this program shows you 100 time steps at a shot. Obviously, very fast to simulate these things. These are just an array of finite state machines, little machines that have a logic function. And so can simulate this pretty fast. And, I guess to the eye, this looks like the same kind of texture. Well, it turns out it's actually quite structured. So I want to give you a little hint of what that can look like. But first, just to kind of state the obvious, let me go back to the initial condition. Same initial configuration up there. I've been talking about periodic boundary conditions, and I can show you what that looks like rather directly. So here, in periodic boundary conditions, site 0 is the neighbor of site 99 on this 100-site lattice. but I can also just change that to display the cylinder that this effectively is. Now, it's a bit of an issue to show that in a flat projection, but here's the same space-time diagram shown in these periodic boundary conditions. So this is the initial configuration in here, and then every ring going out is another iterate. And of course, we can iterate that. So this isn't maybe too much more than just a visual gimmick, although sometimes there are issues about how patterns, a little hard to see sometimes when they move across the linear display, and this can be helpful for that. But now maybe a little more telling and interesting is to adopt this dynamical systems view that I've been arguing for. So now what I'm going to do is do the same initial condition, iterated over the same number of time steps. But now what I'm going to do is the following. So remember, the idea, okay, the view that dynamical systems takes is that the instantaneous configuration of a system is a point in its state space, right? And then as the dynamic operates, we trace out some so-called trajectory or orbit. So what I've done here is actually show you the dynamical systems view of this cellular automaton, right? So what's the state? The state is literally this 100-bit string. Well, how am I going to look at that? So what I'm going to do is think of that actually as a number between 0 and 1, a fraction. And the way I'm going to do that is to break it into two pieces. So if I have a state, this bit string, length 100, what I'm going to do is look at a window of length 20, and I'm going to move that across. And for every window, I'm going to put, think of it like a binary point, so that 10 digits on the right become a fraction 0 to 1, and 10 digits on the left become a fraction 0 to 1. And I'm going to plot those, the right fraction and the left fraction, in this plane. I mean, it's not an uncommon way to look at binary strings in terms of this metrizing it by putting a binary point. There's a most significant bit, least, and so on. You weight those, and then it becomes an integer between 0 and 1. Okay, so here we are, exactly the same space-time data, but represented as if it was a dynamical system. Again, what I mean is the state of that cellular automaton at time is a point here now. And then I operate on it, and I get another point. I operate and get another point. So there's a one-to-one mapping between this view and the original lattice. Obviously, it looks completely different, and actually a little bit suggestive. So what do we, yeah?
I was just wondering, how is time represented?
Successive points here.
Okay.
So I just threw up a bunch of points. I did a bunch of iterations doing this metrizing, kind of left and right half, and then throw up these two-dimensional points. But this is a faithful representation. There's a one-to-one mapping between the original space-time diagram and this. Okay, well, that's kind of interesting. This is a rather different view, but it is this dynamical systems view, which, if you remember, as we first started talking last Thursday, I was sort of criticizing it a little bit, in particular when we study spatially extended systems, because here, to think that the instantaneous state of a system is a point, this is a spatial configuration. That dot is a spatial configuration, and what I really want to do is look at it and say, oh, these sites are neighbors, and there's a texture over here, and there's a domain wall here. But if I think of it as, if I mathematically represent it by point, I throw all of that away. So that's sort of a criticism. Or it's one thing you lose in this dynamical systems view. So I just kind of wanted to drive that point home, that it's a valid, completely valid representation of the system. Maybe less helpful than seeing the space-time diagram. Well, actually, it has certain strengths. So now if you look at this, to the eye, hopefully you'll immediately thought back to the dissipative Baker's map. Remember that? Now that was an even simpler set, but it had these properties of having fractional dimension and kind of nested sets and cell similarity. So in fact, we do find two big blobs. One of those blobs is made of two blobs. Well, one of those blobs is made of two blobs, and so on. So what's interesting about this dynamical systems view, we start to see that this if it's an attractor somewhere here, there's some sort of self-similar structure, just like, or somewhat analogous to the Baker's map. In fact, these are generally called Cantor sets. And what's happening is that there are certain spatial configurations. There are large regions here that are white. We have no spatial configurations that correspond to these points here. And what that corresponds to is that there are restrictions on what the spatial patterns can be. So in this particular case, this is elementary CA 18. Turns out the dominant texture is easy to describe. I'll have to prove it to you in weeks from now, but it's 0, flip a coin, 0, flip a coin as you move across the spatial lattice. It's not an obvious property, and we're starting to see that. What that means is, for example, you can't have 2 ones in a row if it was purely that texture. Right? 0, coin flip, 0, coin flip. I can't go 1, 1. There's always a fixed 0 in that noisy period 2 pattern. So there'll be whole sets of dots here that can't occur, or spatial configuration that can't occur. Those with pairs of 1s. Well, it turns out that's a fair description when the only spatial configurations you put in here have exactly that pattern, nothing else. But we started from a random initial configuration in which all possible spatial configurations can occur, so we're getting some scatter here. Now what I'm going to do is, remember before with the space-time diagram, I iterated again, showing you blocks of iterates of 100. And at least to the eye, it didn't seem like much change in terms of the spatial structure. You know, it's white triangles, and it's kind of, you know, looking a little bit random or stochastic or something like that. Now I'm going to iterate again, blocks of 100, and we're going to see something very interesting that points out the strength of this particular dynamical systems evo spatial system. 3. I just iterate. So now we're probably, it's not on here, several hundred iterations in. And what you notice is that the scatter of states that were out here are gone. In fact, it looks more and more simplified. I'm not quite sure what the right way, it's a little bit simpler. Let me keep going here. Suddenly, boom, it just got completely simplified. Again, this is a perfectly valid view of what that spatial system was doing. If you were looking at the space-time diagram, you couldn't see this sudden simplification. Or I could tell you, well, we need some tools. But here, suddenly, we get what is a very regular, if self-similar set. All the scatter is gone. So just to add some words to this, but at this point just intuitive, we had a bunch of initial transients. Remember, the mapping, the global mapping is dissipative. So the whole space of strings is shrinking down. It means it's kind of throwing stuff away. More restrictions are coming in, like no 2 ones in a row, that kind of thing. And then finally, we end up with what we're seeing now are the spatial configurations that are consistent with this set I just mentioned, 0 wildcard. This is the entire set. And so that simplification means the transients were iterated away, they relaxed, we came down to an invariant set, and you're having to take my, my statement at face value that these dots here correspond exactly and only to spatial configurations that are 0 coin flip, 0 coin flip. Now you couldn't visually see that in the space-time diagram, but now we're looking at the invariant set for the cellular automaton. And generically, these invariant sets look like these self-similar or Cantor sets, these fractals. Yeah?
Is there anything characterized how this depends on how you map state space down to 2 dimensions? Like, I mean, would we see something similar for other maps?
Yes, right. But they can be more complicated. I picked ECA 18 because I happen to know and we've proved exactly how it gets structured in terms of this 0 coin flip, 0 coin flip invariant set. Actually, it's an attractor. In fact, we saw a scatter of states. They all disappeared until finally they were attracted on to somewhere into this invariant set of spatial patterns. So it's even kind of a visual demonstration that we have attractors in this space. Again, this is true. The statements I'm making are actually true of lattices of any size. So it's kind of interesting. There's this way of describing how the self-organization is occurring, almost independent of the dimension of the system, the state space system. So, and then if I keep going, this set, we only see this set. Individual dots kind of hop around because the individual configurations are changing, but their characterization is still in terms of this 0 wildcard.
Has it been explored enough to know whether all initial conditions go to that in the same amount of time, or is there variation in terms of how quickly they get to that final state?
Yeah, there's variation. So very quickly, what we're going to talk about in the spring is that we'll formalize this notion of these invariant sets for spatially extended systems, for the cellular automata. And then those are, in a sense, kind of background states, even if they're, in some sense, random or chaotic like this. And then there'll be what we call in physics excitations, or particles that kind of that ride above that correspond to these domain regions disagreeing on, in this case, spatial phase. So you can have 0 wildcard in this for rule 18, and all the fixed zeros are on the even numbered lattices. And over here, they could be on the odd. And then when those two domains come together, there's a disagreement about the spatial phase of the pattern, and there'll be a little particle. So rule 18 we have analyzed to death, and it turns out that it has only one invariant set, 0 wildcard. You can prove that it's an attracting invariant set, again, independent of lattice size. And then all the relaxation dynamics we just saw, this kind of pointillist picture here that we're kind of relaxing down to the simpler Cantor set, all that corresponds to various kinds of particles that have pairs of ones in them. They kind of violate the background texture of 0 wildcard. They have pairs of ones. So they take different times, depending upon, I'm throwing in this arbitrary initial bit string. I don't know how many particles it's going to lead to necessarily, and it might be none, it might be 100 particles, it might be 3 particles. It takes a while for them to relax. So there's actually quite a bit we can understand about the structure of the state space. They're nested regions of the state space that correspond to having the same number of these alpha particles, and then they pairwise annihilate, and you go from, say, 30 down to 28, down to 26, and so on. So anyway, we'll come back to that. I'm just kind of, I just wanted to correct a little bit how I was introducing spatial dynamical systems, critiquing a little bit the dynamical systems view, this point state view. But there are some useful things we can pull out. Okay.
Hey, Jim.
Yeah.
So because this is discrete, it's a finite fixed set, right? Like this isn't like a strange attractor where you never visit the same thing.
Oh, it's very much like that. So everything I've been saying in terms of summarizing the properties, those are true on the infinite lattice. And infinite binary strings have the cardinality of the continuum. So we have all of, and then there are these invariant sets, and there's near recurrence and all that type of thing. So it's very directly analogous to the.
So on the infinite lattice, right?
Right.
Yeah. Okay.
Yeah, a finite lattice, it might be large. So here we have, 100-site lattice. So the state space is discrete, finite, and has 2 to the 100 members. And because it's finite state, it will eventually repeat, like any finite state machine must. But what we're interested here are the typical properties. So you can, even if you're doing simulation studies, the strategy is, if you're not doing analytical work along the lines I've been describing, you look at the properties on different size lattices and make sure the properties you're studying stabilize on sufficiently large lattices. If I ran this on a 5-site lattice, it would immediately converge to a periodic sequence. So, okay. So now to something similar. Okay, how are we going to do this? Record, and now record and replace. Okay, good. Here we are. Okay, so, right, so we just finished up we did a survey, Monte Carlo survey of elementary cellular automata with radius 1 and radius 2. I showed you what the periodic boundary conditions looked like. The most interesting thing was to take this pure dynamical systems view. Basically, that you can show that this global mapping that we were talking about that maps one configuration to the next, the global dynamic for the cellular automaton, can also has this other representation of the square onto itself, unit square. So now, one small modification. What we're going to do is have the local state space in our lattice system be continuous. Okay, so we call these map lattices. This will be discrete in time and discrete in space, but continuous local state. Now, if we have n lattice sites, the dimension of the system is going to be determined by the local dimension, say one dimension, and if I have n lattice sites, I'll have an n-dimensional system. Right? If I had a d-dimensional local state and then a lattice in 1 and 2 spatial dimensions, we had a very high dimensional mapping. But it's a discrete time mapping nonetheless. We have a neighborhood just like before. Notation gets a little bit messier here than with the cellular automata, but the idea is exactly the same. You could call these cellular map lattices because there's a notion of neighborhoodness here. And what happens is that there's a local dynamic before. I'll still denote this phi. But now we take the local configuration, the dimension which depends on the radius, the coupling from one site to its neighbors, and takes that neighborhood to determine what the value at the center cell is at the next time. So it's a mapping from, let's say, if we had one dimension and it was an elementary cellular system, we had radius, that means we look at our 2 nearest neighbors and ourself, then phi here, it's a function, no noise. Then the neighborhoods are in a 3-dimensional space, and we map down to a 1-dimensional space, which is the state of the site at the next time. And we make the same distinction here. There's this local specification of the system given by this local rule, lowercase phi, but then what's actually happening is we apply that simultaneously across the whole lattice, just like with the cellular automata. And then we have this global map that takes the global configuration over the whole lattice. That's the vector of all the states locally, and then maps to the next global configuration. So why do this? Well, there are some different things, one of which Chris just asked about. The cellular automata are all discrete on a finite lattice, and there is sort of an issue. Are you just looking at some long periodic orbit? Here we have continuous local state. So we have notions of closeness. Basically, geometry is back. We have a notion of closeness between local state values. Before, in the cellular automaton, the closest that 2 spatial configurations could be was 1 site, 1 bit difference. Here, the distances can be arbitrarily small, so we have a nice notion of closeness topology and geometry and so far. The dynamical systems ideas that we introduced already most directly apply to continuous systems, so they apply here. We have all the qualitative dynamics. We can now talk about doing bifurcations. There's a notion of a parameter value that can slowly change to look at bifurcations, even though these are high-dimensional lattice maps. In cellular automata, there wasn't really a natural notion of even one rule being close to another, let alone one way of parameterizing between them. People have tried, but that's usually not very helpful. And if we want to get quantitative, these are continuous state dynamical systems. Therefore, everything I said before about instability, exponential separation and contraction, dissipation, all those ideas, and in particular the Lyapunov characteristic exponent spectrum applies. So these are great tools now. It wasn't immediately clear how to measure instability when we talked about cellular automata. I sort of hedged a little bit about what a chaotic CA was. I mean, visually, Rule 18, Rule 90, they look kind of noisy and complicated. The way I talked about it was to look at what are called the difference patterns. If you remember, you take one pattern and a pattern next to it that's just different by 1 bit, and then you plot in the space-time diagram how the differences grow or not. And if they grew, then we call it tentatively chaotic. Here, we have continuous states. We can actually have exponential separation in a well-defined sense that we talked about already. So old tools we can use to be more precise about what's going on in these map lattices. And there's actually some new ideas. So I'll illustrate these. Before we had, remember with the Lorenz and Rissler, we had maximum X or maximum Z return maps, a way of reducing the dimension from a continuous flow down to a discrete time one. And we're always looking for ways to reduce the dimension so we get some visual handle on what's going on. Well, here we're in n-dimensional or essentially infinite dimensional systems. Any way we can reduce the dimension is helpful. So I'll show you a couple cases where we can use spatial return maps. I look at how one site predicts or doesn't predict the next site as I scan down a spatial configuration. And also now we can imagine that there are little perturbations, they move in space and time, like particles. So, and it turns out that the way we measure the spatial propagation of perturbations, like those difference patterns for CA, well, it'll be clear that spatial propagation of instability is not the same thing as the Lyapunov exponents. Okay, so let's a little preview. So, simple case, and we'll just work through this in a little bit of detail and try to illustrate some of the new phenomena that can occur and how we can apply regular dynamical systems tools to explain how a lattice of maps forms patterns. Okay, so this particular case is going to be the logistic map. Easy to make a cartoon of this. Every lattice site has a continuous one-dimensional state space, the unit interval, and then there's a map. Okay, all across the lattice here, discrete spatial lattice, and then there's some coupling between these that we get to specify. And I'll just choose a simple additive coupling here, typically. So the local state is in unit interval, and then here's one example of how to couple logistic maps. So at every site I, we have the familiar quadratic function r times x times 1 minus x. And what I'm going to do here is just look at the value of the site to the left and right, essentially take the average, and then there'll be a parameter, C here, that gives the coupling strength, how much the neighboring sites perturb the center site you're interested in. Now, why do this? Well, in isolation, we presumably know a lot about what the logistic map does, so it should be a little bit familiar. And in particular, we should know exactly what's going on when C goes to 0, right, when they're independent. Okay, so that's the idea. So, yeah, absolutely.
It's on the previous slide. So, when you build the global space, you don't take the metric of the lattice into account. I was wondering if it's possible to construct the metric of the global lattices. Is it possible to take the lattice metrics into account to interpret it?
Okay, I'm missing the word. Did you say metric?
Yes, I'm saying metric. In other words, if 2 points are close and they differ, they're close in the lattice versus if they're apart, we don't distinguish between them.
Right. Yeah, so in the case, and we were kind of talking about the metric to use for cellular automata, when I presented that XY plot on the unit square, and I made a choice. I took, there was a window of 20 sites. I took 10 on the left and put a binary point in front of that and call that the X value. That then makes it a number between 0 and 1, right? And then, so I'm metrizing it by, there's a, most significant, next most significant bit, and so on, and they're weighted by powers of 2, and same thing with the left half, and calling that the Y coordinate.
Right, but in the more general picture where you have, the state of this real or some kind of eight-dimensional state in every point of the lattice. Now you want to view it as a global system where you take, R to the ZD or something as your state space.
Right.
And then you're just taking the metric, like when you're talking about dynamics, you're using metric in this state.
Right. Well, here, just think of Euclidean metric, like for the logistic map lattice. Right. So at two different spatial configurations, there are a vector in the lattice has n sites and n dimensions, and we'll just use the Euclidean measure of distance.
That's right. So I'm wondering if I wanted to think about the metric of the lattice into the
Oh, you mean for the map lattices, could I do this, what I call the dynamical systems plot? Is that the idea?
Well, assuming the Euclidean metric rate of two systems differ by the same amount in adjacent
Right.
spots, it's going to be the same distance as if they differ like across the space. And using unrelated.
Oh, right. No, I see what you're saying. Right. Well, okay. So that is kind of the idea. Right. So just to kind of bring this together. Right. So if I have my n logistic maps on a lattice, and they're two different configurations, I have these two vectors, and it's sort of very the distance between those is not weighted by how spatially close they are. So that, I mean, exercise, a good idea. I'm trying to think about how you would do that. It's essentially what I just said. If there's some way, and I'm not sure I'm going to propose a particular idea right now, but good to think about, what would be a good way to adapt that binary string metric to this case? Okay, one way we do that, but this is next week, is we can take the continuous system and actually replace the continuous state with discrete symbols. And then in a case, we would take the map lattice and turn it into it's called symbolic dynamics. We will get to this. Then I would have the sort of data from the map lattice, the spatial configurations would now be discretized, and I could directly use that previous metrizing to think about this mapping of the square onto itself.
Okay, I'll wait until next week.
Yeah. No, it's a good question. No, but other than that, I'm a little bit, it's a good idea. It's a good idea.
Well, I mean, I was thinking that they, instead of embedding just a single point as its value, you take a letter dimension, you could take some kind of neighborhood
Yeah.
and use that as
Right. Yeah. Yeah. Well, I'd be curious to see, how helpful that was. Not hard to program up. I mean, all of these cellular automata and these map lattices are very easy to program up, and maybe it's mostly just an exercise in some graphical programming to see if it's insightful. It's a good question. Okay, so, but how are we going to think about this, right? We have the logistic map. We know as a function of R, it goes through this period doubling sequence and chaotic bands, and period 3 and period 5 windows in the chaotic range and all that sort of thing. Question. As I start to couple these period doubling systems together, how do they interact, and what's the consequence for the kinds of spatial patterns they can form? Is this just going to be, I imagine I'm kind of weak coupling. C is relatively small here. If it's small enough, you might imagine that as I sweep R, I'm going to get the full period doubling sequence, and the neighboring maps, say if they were uncorrelated, they just add a little bit of noise. So kind of a first guess, which is just relying on what we understand already, imagine as a function of R, we have a kind of a noisy period doubling bifurcation diagram. Okay. But first I want to suggest maybe something that's a little more fundamental change in perspective here. And it hints at the essential thing that adding spatial extent does to dynamical systems. So what we're going to do here is simplify things a lot just to get started, and so we can visualize what's going on. I want you to just think about two coupled maps. So much for my talk about infinite dimensions, but this is just to get us thinking about what can happen in the full lattice. Okay, so we have two coupled logistic maps. So here we're going to have the same parameter value. So I have r times x, 1 minus x, and then the second map is r times y times 1 minus y. And then I just cross-couple these with the same coupling strength. I just add in the other map to a given one. Let me set the r value here to actually right at the onset of chaos. As if C was 0, the individual maps would be right at the end of period doubling just before chaos. So that's 3.56995, so on. But I'll add a little bit of coupling. 0.005, just a bit. That's pretty small. So, again, if the coupling was turned off, we would know that we had this period 2 to the n orbit here. But now what happens is that we've added a small contribution from a neighbor. And what that does is because it's small, it just takes the map and offsets it a little bit. So think about those green humps I drew before. A first approximation that they input from the neighbors just shifts it up a little bit. It's like a constant offset, which is intuitively going to, maybe you might think, push you a little further into the, past the period doubling into the chaotic regime. And that's roughly what happens when I add this coupling. So what I'm showing you here is the X map and Y map coupled together. So again, the state space is now the unit square. And it turns out that what we end up with, if we just offset one map, we'd have these banded chaos attractors. But when we look at the system together, we have different attractors based on the relative phase of the two. I mean, if I just looked at one map, I kind of forget that, say, if it was a period 2 orbit, it was, at even time steps, the value was high, odd time steps low for a period 2 orbit. But now when I have another system coupled in, what becomes important is the relative phase difference. If one is period 2 going high-low and the other is period 2 going high-low, then they'll, in a sense, be along the diagonal, but they could also be out of phase. So one is going high-low, the other one's going low-high. And that corresponds to attractors off the diagonal. So in this particular case, with this setting of the parameter values, in fact, what you find are let me get this right. 4 different attractors, all colored differently, right? So we have pink, green, blue, and red. Those are all distinct attractors. And the way, and why this many? Well, it has to do with the relative phase. So the individual logistic maps have been pushed by the input from their neighbor up to be more chaotic. So it's essentially like 4 bands. So if I were to project this down onto just the X map, I'd see there are 4 bands like that. But it's not in isolation. The actual state of the system depends on the phase and state of the other map too. So the pink 4-band attractor corresponds to the 2 maps tracking each other, although there's a little bit of chaos and they're sort of separating from each other and coming back, but they're constrained. So there's the in-phase attractor, and then there's the exactly out of phase, attractors, I should say. The blue one here, right? So one system is oscillating high, the other one is low, and then they kind of switch back and forth. And then those oscillations are modulated a little bit by the chaotic behavior. So even when we have 2 coupled maps, because the relative phase becomes important, and this particular system, the logistic map, is generating very high periodic orbits, there are all these different choices of initial relative phase that lead to different attractors, different basins of attraction. In this particular case, we have these 4 distinct attractors, depending upon how we set up the initial phase. You can play around with these parameters, so it's kind of a quick conclusion. If you play around with the parameters, lowering the R value or decreasing the coupling a little bit, what happens is that you can jigger the parameters so that you essentially can see the period 2 to the infinity orbits. And the consequence is you actually have an infinite number of attractors in the 2 coupled map case. Puzzled looks. So is the basic argument clear, right? The idea is, again, just think about each map just being period 2. Okay, so each map is either high or low, and there'll be, and now imagine the global system is periodic, there'll be 2 distinct periodic orbits. One periodic orbit, period 2, where they're in phase, they both go high-low together. High-low together. And another where you chose the initial conditions, so they're exactly out of phase. They're not so strongly coupled that their behavior is knocking them out of being period 2. We're assuming they're still period 2. One is high, one is low, and then they oscillate like this, out of phase. So there'll be an out of phase, off diagonal attractor, or periodic orbit, period 2 orbit in that case. So I'm just drawing out the consequences of that observation, that now you imagine it's period 4. Well, okay, I've got A, B, and C amplitudes here, A, B, C amplitudes here. I got 4 choices here, and there's 16 possible relative initial phases I could have for the period 4 orbit. So I'm going to have 16 possible different attractors, period 4 orbits, depending upon my choice of initial condition. And so you should think of these things as like little basins of attraction here, and it just ramifies as I move the system further and further up to see period 32 in each, period 128. Suddenly this state space becomes riddled with all these small basins of attraction that correspond to the different choice of initial phase for the orbits. And then the same argument works up here for when we have chaotic bands. So here, in some sense, we have 4 chaotic bands, and we have a choice of initial phase. So in this case, we get 4 different attractors. Yeah.
So eventually they'll become one band as well, right? In that case.
Yes, as you increase R, right. So you can now try to imagine. It's harder because we have a 2-dimensional state space across R. Well, this is doable. We have fast graphics cards, so in principle you could render this object in 3 dimensions and look around. And there should be some analog of band merging where you would sort of suspect, given the closeness of the red and blue attractor, if I increase the coupling a little bit, it's conceivable. I'm forgetting whether at this parameter value it's true, but I see a little bit that these would merge, and then I would just have one off diagonal and one on diagonal band attractor, right? Yeah. So this is the basic idea to understand these spatially extended systems, these map lattices. That suddenly, the new thing is that relative phase, which we've been ignoring before. I never really even mentioned what initial condition we were using. In fact, I kind of, doesn't matter where I start, I end up on the Rissler attractor. Here, when you're starting to compare two systems, the relative phase is important. And it's the relative phase in a spatial system that makes it do its unique things. Like relative phase difference can support propagating perturbations in space, for example, traveling waves and things like that. So phase becomes important here. Okay, let's shift back. Let's see if we can take that n equal 2 case and help us understand a little bit what's going on for a spatial lattice. Here, and it's a logistic lattice over 256 sites, periodic boundary conditions, just like for the cellular automaton. And what I'm going to do here is, over space, just start with a sine wave initial condition. And this will help, I think, emphasize the argument I was just making. R equal 3. So if you remember R equal 3 for the isolated logistic map, that's right where that non-trivial period 1 orbit goes into period 2. And then 0.05 coupling. Okay, so this times 0. Again, 256 values, setting the initial local state at each of the 256 sites. And then I iterate it 10 times. And I end up with this almost square wave-ish looking spatial pattern. So what's going on here? Well, you can imagine that, say, the lattice sites around here have relatively similar initial value, and that, and we're somewhere in this period 1, period 2 regime, if these are close enough, their differences will actually will decrease over time, and they'll start tracking each other in their period 2 oscillation. And that's what we see. There's a range up here where any initial differences after 10 steps basically go to 0. This range of sites, these are all exactly in phase and have pretty much the same value on the interval, same amplitude. Same thing over here, so apparently it didn't make that much difference that I started with large values here. And then now I have these two regions that are in phase. If I were to show you time step 11, I don't have that. Time step 11, this would exactly flip over. Then there were another set of points, I should say sites here, that, again, their spatial differences decreased, and they made another region here of sites that were in phase, except the phase, the high-low phase, here differs from this. So you end up with this period 2 oscillation. So then just keep iterating. Here's what we get for 20 iterations and 30 iterations. And what you see is that the region of in-phase sites gets larger and larger. They're sort of entraining their neighbors. And in a complementary way, the sites between these homogeneous regions get sharper and sharper. So just to introduce some terminology, I call the in-phase sites a domain. This would be another domain. This is a domain down here. And then between the two domains, there's a wall. So the wall is where the sites are sort of disagreeing, or they're being pulled in two different directions. They have these neighbors that are doing this. They're out of phase, and they're being pulled this way and pulled that way. And then over time, it just gets sharper and sharper. So you can actually calculate the values of these sites. I mean, there is a periodic orbit that this 256-dimensional system map is going to, and you can make various approximations to calculate what values these sites will go to here and here. So let's look at this in space-time. Okay, so this is just like the cellular automata, but now I have space. This is 128 sites versus time. You can see, so I'm starting with the sine wave again, so it's exactly the same system I just showed you, initial condition and parameter values. So immediately you can see there are regions here where the system is temporally periodic. Green, blue, green, blue, green, blue. And that, in particular, the sites that weren't in either domain get sharper and sharper and sharper up until about here. It's 127 steps. So I just showed you 30 iterations up to about here. I end up with these domains. So this domain, call it even phase. This domain is odd phase. They disagree, and where they disagree, I'm calling this a wall. Then now the other interesting thing that happens is that later on, the wall actually becomes unstable. So we have these regions in-phase regions getting larger and larger. They're sort of pulling in the sites that are on the boundary between the two, get sharper and sharper, but then that ends up pushing the system into, maybe you can see this, it's actually a checkerboard. So period 2 in time and period 2 in space. So in an interesting way, it's almost like the system is kind of having, over in time, going through a series of bifurcations. So again, initial sine wave pattern, in-phase domains grow in size, recruiting their neighbors until the walls get so sharp that, in fact, what happens here is the walls are zero width. But then that means there's a cell that's looking to its neighbor that has a very, very different value, which is a strong perturbation to that edge cell. And that drives this instability, and then I get this checkerboard pattern, which eventually dominates the entire lattice. So we go through domain formation, walls, and then the walls are such a large difference, it drives the system into a different dynamic. Yeah?
This is very reminiscent of like an icing model without the randomness.
Yes.
So, I mean, can you define like a free energy or something like that?
Yes, you can do that. It's often, we'll talk a little bit about that with the symbolic dynamics. Yeah, how there's what's called a thermodynamic formalism as a way of thinking about energies here. Yeah. There was another companion lecture to this, which I'm going to drop, but maybe, based on interest, that was going to go through Ising models and various kinds of stochastic spatially extended systems. So here, these are all just deterministic again. Okay. So now what I'm going to do is just to show you, this is, again, just kind of a little tour of the phenomenology, trying to explain as much as we can based on our knowledge of the period doubling structure of an individual map. So I'm going to increase the parameter value R, so the map is taller now, to 3.4, then a series of diagrams here where the coupling strength increases. Okay, so here, more or less similar regime we had before. Coupling is 0.02, and I'm showing you, starting with the initial sine wave, like I had before. This is a very big lattice. This is 0 up to 2,048 sites. 1,000 steps in. This is the spatial configuration. So we talked about this. We had now these in-phase domains, basically recruited all the sites. So every site in the lattice pretty much is either in one phase or the other and agreeing. But you can see here, it's sort of like a Gibbs phenomenon in Fourier analysis. You can see because these two sites are out of phase but close to each other, the difference between them is quite large. So the coupling is quite strong driving. So we get these little spikes there. In fact, if you went out to maybe 10,000 iterations, you'd see what I just showed you before, that these walls would break down into a checkerboard and have their own interesting space-time period 2 behavior. But here, what I want to do is take a snapshot after 1,000 time steps, iterating the initial sine wave, and then sweep coupling. And what we see here is actually a type of, as we increase the coupling strength, a kind of period doubling and then band merging. So here I'm going to go from 0.02 up to 0.05 in the coupling. And what you see now is instead of having period 2, there's actually 1, 2, 3, 4 phases. And consequently more, domains here. And so one of the things you notice in one of the larger, in the lower coupling, was a single in-phase domain is now broken into several in-phase domains. Every site is going through period 4. But here what happens is you notice these have different sizes. That has to do with how that sine wave initial condition passed through the attracting part of the period 4 orbit. Right, this sort of, how to say this? These sites here correspond to the bottom part of the sine wave, and they were close enough that they all went to the same phase of the period 2 orbit. Same thing over here. And then in between, we had points that were attracted to the other phase of the period 2 orbit. The same thing is going on here, except now, as I vary the amplitude in space, it's crossing over the regions in the local state space where I'm attracted to one or the other phase of the period 4 orbit. And then we get these different size domains due to that. Anyway, keep increasing. So now they're more strongly coupled. 0.06. What you see is we've lost the periodic behavior. Now it's noisy. In fact, it's 4 bands noisy. Overall periodic, but now with this chaotic modulation until I go up to 0.075, I have basically 2 bands. Okay, so this is sort of a contrast or a similarity with before. I was arguing if we had weak coupling and thought about the behavior as a function of increasing R, so using the ideas of the picture we had for the period doubling, then I could explain the number of attractors in terms of relative phase. It's period doubling dominates. Then here, we're fixing R and sweeping C, basically just increasing the amount that the sites perturb each other. And in a sense, it's just shifting each local map further into the chaotic regime. And we see this period doubling as a function of coupling strength, not R, but coupling strength, and then band merging. And the parameter values where this happens, the actual values of the amplitudes can be calculated in terms of what we know about the period doubling behavior of an individual map. Now, what's interesting about the logistic map lattice is that there's something else that happens. There's something new that we can't, that's not in a sense anticipated, extending what we know about the period doubling behavior. So this is what happens actually if you go to very long times. Think back to that space-time diagram where the walls broke down to the spatial period 2, temporal period 2 checkerboard. That comes to dominate the entire lattice. So here I'm showing you, starting from a sine wave initial condition, iterating for a very long time, r equal 3, c equals 0.05, we end up with, so this is a 100-site lattice, spatial period 2 and temporal period 2, oscillates there. So this is actually the long-term behavior that the system tends to go to. And if I were to do a spatial return map, so I'm just, think of this as if it were a time series. I simply plot the next site value versus the previous site value. You can see there are these, well, actually 5 points here. Turns out that there's actually 2 domains here. So that's actually why there is this 5th point. This isn't shown here. It's from a much larger lattice. There's actually the even sites are up, and then it reaches a place where the even sites are down. So there's a disagreement in phase. We get this shift like that. Now, if I increase the coupling again so they're more strongly coupled, 0.075, and again, go out for a long period of time, the system is mostly periodic, except we get this very interesting spatial modulation here. So here I'm showing you a larger lattice from 0 to 2048. And then what we do is the same type of spatial return map. So here we had spatial periodicity, and we saw points up here. Here, if we do this, what we see is actually a quasi-periodic attractor. So what happens is that in the logistic lattice, and this is not something that we anticipate, things that are period 2 and bands and so on, I can concoct an explanation and even think of a way of calculating properties like I've been talking about. But this spatial modulation is actually quasi-periodic, and we end up with this essentially like a torus attractor here. So that's a time scale that actually I still don't know how to calculate. And if you watch this over space and time, what you see is that the phase. So I'm plotting basically relative phase here, and it's cycling around like this. That corresponds to waves, amplitude waves, propagating across the lattice in time. So we actually have traveling waves here. So before, everything I was saying was just trying to use the period doubling picture, the dominant thing, period 2, period 4 bands. I was using that and arguing, oh, they're perturbed a little bit, to argue for phase is important in many different attractors. Now here, this is completely new behavior, unanticipated. I'm not aware of any aspect of the period doubling nature of the logistic map that would lead you to think of these traveling waves and this quasi-periodic behavior. So new things can happen. Okay, so this was a bit of a shift. I only made one change to cellular automata. We just added these logistic maps to each site. Logistic maps, something we understand quite a bit about, and we can explain a fair amount of the behavior in terms of what we know in this sort of weak coupling limit. The local dynamic, the period doubling behavior dominates there. Phenomena, period doubling, appear in space-time and are interpretable. Something new, there can be an infinite number of attractors because relative phase is now important. And then we have these domains of in-phase sites and walls between them. So now when strong coupling, we get this new behavior, this quasi-periodicity in traveling waves. Okay, so let's do one more example of a map lattice. In a sense, this one is simpler, but perhaps we don't have the same intuitions about how to explain what's going on. But certainly haven't studied it so much. So I call this the dripping handrail. So the name comes from imagining that you're in, I guess, a couple months, you're in downtown San Francisco and the fog is in. Right? So there's a handrail and there's water accreting on this handrail, and you get this sort of extended meniscus under the handrail until some drop, until there's so much water that it drops off and becomes thin again. So it's very simple. Again, we have some local function of the state space. State space will just be the unit interval again, and we'll do a very simple coupling, just like we did before, essentially the average of the two neighbors on either side. But then the local function I'm going to do is piecewise linear. I just have an offset. At each step I get a little offset, and then there's a constant slope. Then mod 1. So the way that looks like, so focus on an individual map here. So here's and I'm drawing the sort of the temporal return map, if you will. I have the identity here, and then the green is what this function f is doing. So at each step, if I start with some initial water thickness, it gets thicker, 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 thicker until it reaches here, and then it resets. That's when the drop falls off, and then it starts over again. So really simple. Some people use this model as a discrete time, discrete space analog of what's called an integrate and fire neuron. All that's happening locally is it counts up and resets, counts up and resets. Pretty simple. Now what we're going to do is couple these together in the spatial lattice. Okay, I will explain what's going on, then we'll do a demo here. So this is the space-time diagram. So here we start off with a random field, initial configuration, random values, from about 0.2 to 0.8. And then what you see over time is, well, the first thing that happens is this sort of random, if you will, sort of unphysical initial condition. If it was a configuration of water, I wouldn't have just random values next to each other. It kind of smooths out due to the coupling, and then everything increases in value. That corresponds to the water layer getting thicker and thicker and thicker until you reach some thickness where the drop falls off and the lattice resets to 0 and it counts up again. Gets thicker and thicker and then drops and drops. So the drops correspond to these flat regions here. And we sort of see the same type of behavior. There are regions that sort of are in phase or they're growing together until they all kind of drop at once. There's a little bit of, you notice where the drop happens, there tends to be a site that goes first and it sort of unzips. If I had a layer of water under the handrail, one side drops first, it tends to pull the other neighbors along with it into a drop. Overall, there's, at least initially here, sort of a semi-periodic behavior. Yeah?
So the green represents high density water, a lot of water, right?
Purple does. So it grows, drop.
Right, okay.
Grows, drop. Yeah, sorry. Should put a sidebar on that. So the individual, the map in isolation is trivial. It just counts up and resets, counts up and resets. There's a little bit of a dependence on what that period is as a function of the offset and the slope. But it's easy to figure out. So in a sense, what we're seeing here is the interesting behavior seeing is almost purely due to the spatial coupling, not dominated like with the logistic lattice in terms of local, the local site, isolated site dynamics. One of the interesting things about this system, and I'll just summarize this here, then we'll do a demonstration. So for small lattices, 5, 6, 200 or 300 sites, something like that, some range on the order of hundreds or smaller, all of the initial conditions are ultimately periodic. So what we were just seeing in that space-time diagram are these sites kind of jostling for trying somehow to get into phase. And when they finally all get into phase, then the whole lattice is homogeneous. There are no spatial differences. The dynamic reduces to that of the isolated map because there's no spatial difference, and it just kind of hops along together. The curious thing, though, if you look at how many iterations it takes to get to this periodic orbit, it grows as a double exponential. Again, this isn't obvious. It's just the result in analyzing this, which makes it, this kind of scaling behavior as a function of system size, makes it a little bit problematic to think about getting to the attractor. In the Russell and Lorenz, that all happened very, very fast because there was a large dissipation rate here. This system, imagine I had n equal 100 or 1,000. We're talking about universe lifetimes here. So we used this model a number of years ago to sort of argue this whole notion. For spatially extended systems where you have different regions sort of competing with each other to who's going to dominate, who's going to win out with the phase, that the transients can be so long, you'll never, ever practically get to an attractor. It's almost all transients. So let me show you how the system works here.
Are you saying for just the dripping Handrail or for these lattices?
For the logistic map, the transients typically are rather short compared to this. So what I'm saying is it's not a general result that you have these extremely long transients. It's just a question that you now have to think about. So a lot of the earliest work in dynamical systems was concerned with trying to describe fluid turbulence. A fluid is a spatially extended system, and there were these competing hypotheses about what the right mathematical framework was. So Landau comes in and says, oh, it's quasi-periodic attractor. As I'm pushing more energy through the system, the turbulent response is just more and more harmonic components. More and more quasi-periodic components, irrationally related frequencies, and so on. In the 60s, through Lorenz and some other mathematicians, like David Ruel, the idea was, no, the turbulence is actually one of these strange attractors. So a group of us ended up showing in the early 80s that it was, in fact, strange attractors that described the first stages of turbulence, what we call weak turbulence. You're not perturbing, not pushing too much energy through the system. But then we got kind of suspicious about the whole framework, and then sort of argued that there are regimes for spatially extended systems where the whole notion of getting to an attractor is practically irrelevant. So that's some of the background arguments for looking at this. So let's see if this is going to be the right shape. So the dripping handrail is this guy. So I'll start off with just a random configuration of water. So there. So 128 sites, periodic boundary conditions, and then I'm just plotting the site amplitude. And if I do this right, let's see here. Okay, and then if I can do this, oh, it's not going to let me do this. Okay. Oops, don't do that. There. So I'll just show you the first couple steps. That's just a little hard. These are single iterations. Now I'm going to clear the past two, so that initially very jagged spatial configuration, you can see it's starting to smooth out. If you want, it's at least physically intuitive. I started with a very unphysical, random thickness of water, and the water's just sort of flowing and smoothing out. There, so you can see it's getting thicker and thicker and thicker, and smoother and smoother and smoother. Until there. So it finally reaches the threshold up here, and then, again, that water drop falls off, and now that site has zero thickness. And another site goes and drops and so on. Okay, so that's what's happening in amplitude versus space. Let's go back to the initial condition, and I'm going to change the view to space-time diagram. Okay, so this is the time zero, the initial random water configuration. And just to show you, this is what we were doing before. So that initial smoothing out is what's happening here. We just looked at that, about 10 steps, but we can just go ahead and let it run. So initially they were more or less in phase, but now that's starting to shift. In fact, if you try to analyze this with the usual techniques, sit at a site, look at the time series, look at the structure of the spatial configuration, Fourier transforms, it all looks very, very noisy. In fact, we use this to model, it's called an X-ray binary star system, the first time periodic signals called Scorpius X1. And there were, that's neutron star, companion star. The companion star is sloughing off mass. Conservation of angular momentum has that mass turn into a disk. There's radiation pressure from the neutron star that pushes the inner lip of the disk away. And so our picture was that the inner lip is sort of like the dripping handrail. Mass builds up until it overcomes the radiation pressure, falls in. The mass accelerates and hits the surface of the neutron star, and that was explaining the X-ray bursts that were measured. The competing models were doing basically a rock-by-rock simulation of the accretion disk, and this was able to actually exactly, it was uncanny actually, predict the observed power spectra from the star. So, very simple model. Yeah. The detailed modelers were not very happy with this back of the envelope dripping handrail. But allowed us to make a number of predictions about the physical mechanism. So. And if you wait long enough, you'll see there'll be occasionally these very large regions of the lattice all start to agree in phase, and then they break up again, moves around. And then the strange thing about this is that it will just suddenly, out of nowhere, get close to a large drop, in a sense, and then go periodic. So it's very difficult to predict in time when the system is going to become periodic. That is maybe a contrast with this elementary cellular atomic 18 that has these little particles that move around that pairwise annihilate. Once we discover how to recognize the particles, we can just count them up and say, oh, we just lost a pair, and predict pretty well when the system is going to become a homogeneous background. Here, there is little or no historical information that presages when the system is going to become periodic. It just drops in suddenly. And that has certain consequences for the structure of the state space, the organization of the state space. But we'll have to get back to that once we start to analyze cellular automata. I need to introduce some ideas there so we can think about the organization of these infinite dimensional state spaces. But basically this thing will just keep running and running and running like that. And then, boom, all homogeneous periodic, spatial periodic pattern. Okay, so I went a little slow today because I wanted to finish up talking about these spatially extended systems, but maybe just make a few comments about where we're going next, because so far you've had one impression of what the course was about. That's about to change radically. So what I want to do is well, it's saving, that's a wait, is give a little bit of a heads up for the next lecture. So the reason we were studying dynamical systems was not so much for the interest in the ideas, although people do this for their livelihoods, but I wanted to give you, I want to use the word concrete, but this is sort of abstract and mathematical, but a picture of where randomness comes from. Why do we use probability? So that's the next topic. We have these dynamical systems that are, quote, chaotic. We have ways of being quantitative about the degree of instability with the Lyapunov exponents. But what are, in a sense, what do these systems look like when we attach an instrument to them? So basically today, we're going to close the black box, the gray box up, and just look at what these systems can produce. Why would we, in looking at these systems, want to use probability theory? So just to kind of remind us, so this is the cartoon summary of the entire course. And so far, we've had our heads stuck in the box. We can see the state space in many different ways. We have this detailed view of complicated orbit sets, but that's not how the world is presented to us. We have this indirect view through some kind of measuring instrument. So we're shifting now. Start talking about, first, how in dynamical systems probability theory naturally arises, and we need to generalize the notion of invariant sets and attracting invariant sets to invariant distributions, show what the benefit is of using probability descriptions of dynamical systems. And then we're going to introduce a theory of measurement, how finite precision measurements of a chaotic dynamical system lead to the system appearing to be stochastic and random. And then this will take us into information theory. In some sense, we have sort of much less geometry. We're going to focus on how we can measure how complicated the measurement streams are that we get out from a chaotic system. And then spring quarter will be sort of over here when we go back and ask the more challenging question, is there some way to go from the measured data that we now know how to talk about in terms of different kinds of information production and information storage, is there actually a way of going back from the data to see what the internal dynamical system is? So that's going to be spring. So now we're going to shift into probability theory. Next lecture, measurement theory, and then information theory will sort of carry us through the winter. Okay, so I'll stop a little bit early today if you have any questions.